Yeah, they haven't got much to,
There's always something
you know,
to check here. It's always like, I don't know why. I keep this one at my desk in case someone doesn't turn off their mic. I can mute them. I don't know why. I don't know why we don't sound, but they can hear it.
Any chance I could take a look through my slides, make sure that.
Yeah. There.
Had
Don, is your speaker muted? Maybe that's the thing.
Able time. Perfect. I think that was
So it's awesome.
because they're something.
Okay. Okay.
Engineering, I don't know how you capture.
I need to open all the
That's a good.
every slides. Open up here. And we can't hear them, not sure why. But I'm not gonna start now.
Huh.
It's another option. You want to use this, you can. Which I did. I'm so quite so. Since it wasn't. You listen to Black Rock.
Okay.
Thank you.
I don't think his microphone's muted.
Yeah, it wouldn't be his
It would-
microphone. Now that I've sent that, I realize it.
Yeah, it says speaker. Pour me a cup of coffee too while you're at it. Tempted to get up and get a glass of wine.
Well, as soon as the meeting starts, I'm going to get up and get my dinner and then
Yeah.
and shut my video off so you don't see me eating.
Oh, we just got back from dinner. I live at Woodcrest Villa, which is a senior community in Lancaster County now.
Oh, you're in Lancaster. Oh, okay.
Yeah, and they serve us dinner every night. Actually, they serve 3 meals a day.
That's
But
nice.
Marilyn and I usually only go for dinner. Of course, you got to pay for them. Oh, I like that picture.
I have 2 slides before yours, then you can,
Okay.
then you go.
I
Yeah.
think I'll do that with mine too.
You still gotta hand out some stuff.
Yeah, since I'm at an astronomy club meeting, I might as well look the part.
There you go. That's better. I think Don wants us to communicate through the chat.
To do that.
If we had anything to say, just go through the chat.
Oh, here I'm clicking on the screen and it's on his computer.
I can watch it. It's supposed to be killed. It's I got spot as you listen to it also. Well, that's the clear. If I was, yeah, it's not a time watching. And I also had a short way up, so that short way going, where we get this in split the gun. I think it came off pretty good, right? I have to get these off these, what counts. To be like, and see you're having just the reading. Right out on the John is the one who's the first version. Yeah, but you know, Red Skater, door to the base race, drive in, back. We were suddenly more out. We have all my life now. And it would be one of my children. We got one much with her, but that's not gonna happen. That we come up with the first time I'm ringing, that's a little bit, that's the plan for. Computer usage or the one. You're like, you go around, we've got little one, it's like. We're gonna get out of the city, okay, place, it's, you know, he's.
First, you can give the rich blessing, sitting right behind you there.
I wouldn't even bother coming with my suitcase up here, it's still not.
Are you set for the 21st
Yeah.
of February?
Yeah, we have like,
Do you need me or?
a couple, you know, we have 6 or 7 people.
I saw that.
We're in pretty good shape.
Okay, well, I don't wanna there's not stuff on people.
Oh, no, it's fun. It's on the but you know, we can get by without. Want to join us, that's fine too.
Not at all.
Okay, but we have plenty of. Now, so.
Right.
They're all two from that, so I'm like, yeah. The death trap, yeah, right down, yes. We got to get that worked out yet, yeah. Even the mood will be a chat. Okay. Yes, it is. Oh, we got right. That's closer to the sun. Sort of things.
You can't hear.
Because almost over, huh? Over.
Can't hear a lot of people. Again, we're also.
Well,
Technology. Yeah.
yeah, we'll have to remind
What they can tell, they'll get your.
you know what?
Yeah.
Yeah. It is the same with that technology. Yeah.
Becca's thing is ready, but we're good to go.
Can you hear me?
I mean, when I got that lot there, John.
Live streams going.
Ratio one after another, sub up. And the other thing is. Yeah, one mine on that too. I saw that.
All right, let's get this meeting started. First of all, I'd like to thank everybody who braved the heat wave here that we're having right now. To come out on this balmy night, I mean, good lord, I was tempted to go out last week, one night when it was clear and Jupiter looked beautiful. I stood outside, I think it was about 9 degrees or so, and the wind was going at 20 miles an hour. I was like, nah, it ain't happening. But anyway, welcome to the February meeting of our society, and we're gonna have a great meeting tonight. A very exciting speaker tonight who we're all looking forward to, and that should be a fascinating talk. One quick item of business. First of all, I'd like to thank all of the members who contributed to the scholarship fund for this year. We have enough that we are able to do another 3 grants to deserving students. Again, thank you for everybody that chipped in, found generosity. And it really does cement our relationship with the university. So thanks again. We're in great shape, and Bruce, we're looking forward to finding out which students are going to be getting the awards.
Right. All the info will go to Mark Gagne. The committee will start meeting. They'll get the applications and.
Fantastic. So again, great job, everybody. Let's keep up the great work. And sometime in the near future, I believe we're going to have somebody come from the endowment fund to talk to us about it, how it works, what it is, and just as maybe a pre-meeting talk to kind of give us an idea of what we're doing. So with that, I'm gonna turn the meeting over to, are we doing great, Scott?
Yep.
Okay, I'm gonna turn over to Don and we're gonna see what's up.
Just real quick thing, I have one slide, then Don Miller comes up. Again, we have our beginner, let me hide this thing here, okay. I don't want to hide, I don't know why. Beginner astronomy classes with Chester County Lifelong Learning, used to be Chester County Night School, March 18th, 22nd at First Middle School. Our members can attend free. You don't want to register with CCLL. Just send me your name. Right now, we're up to about 20 or 21 students, so we're in really good shape for the classes. Ooh, back up. All right, Don, you're up.
That was brief.
Yep, go ahead.
All right, good evening, everyone. Just a quick observing highlights. Let's see the arrow here. There we go. Basically, planets this month, we've got Mercury greatest elongation on the 19th. Hopefully, if the weather's warm enough and you want to brave like Dave would to go out there to try to look at it. Venus not visible till month's end. We're going to have another parade of planets if that's something you're interested in. Mars not visible. Jupiter, fantastic. You know, we're still at opposition. So it's a great time to look at that. Saturn, low in the western sky, early evening, setting pretty early. Okay. Uranus visible till 1 a.m. and Neptune about till 9. Okay. So planets are challenging, especially as I've tried to plan our outreach events this month or this year, excuse me. You know, getting a good weekends with have planets and have also the moon also in the right spot has been a challenge this year with the timing. As far as night sky objects, I mean, I just love this time of year. I can remember one of the things that I fell in love with astronomy was seeing Orion Nebula and the Orion constellation. It's just spectacular, wonderful just to look at it with binoculars. If you get in a dark location, it's amazing. The Beehive, of course, is a wonderful open. Pleiades, another one, and then the M35. So some really nice open clusters to look at this time of year. So if you can get out and do it. And of course, photography if you have the equipment. Outreach updates. So February 9th here today, solar outreach, we have 60 events planned. Okay. Just a few this year. Okay. Roger is cutting back. I'm just kidding. He is sort of cutting back. He probably would have had more. We've only had 4 club members respond to help with the solar work. We don't need people at every solar event, but to really do some of the key events, we probably need about 5 people at a solar event to actually be able to work with it. Roger's a team with his wife, so we need at least 3 others to actually do it justice. So as I said at the last meeting, I really need club members to step up. And so we only have 4 so far. Nighttime, we have 17 events planned for outreach. This doesn't count the club events, okay? Only 10 club members have responded to my request for help so far, okay? We have like 180 plus members in this club, and we can't burn out the people who are coming to these events and putting out their telescopes. You know, of the 10 people who have responded, most are at the one event, okay? So most of our events have no one or one person who we have at the events so far. So I will send out again the list of events this year, and it does change. So I've got another event added from what I had last month. But I'm asking you to please take a look at it and see what you can do. Yes, Dave.
Does the Google link now work?
It does. Well, the Google link should work, but I'll just send out the file that's just as a separate file so they can fill it out and just send it to me.
Because I did look at the Google link and I was having trouble.
Google's really challenging. Let's put that. I'll be diplomatic. Okay. Key takeaways. We can't run our events without adequate club support. Okay. If I have to cancel an event, I will, but that doesn't help us. Our remit is outreach. Okay. So we need to be able to do that. And then it hurts our reputation. We have it with the Park Service, etc. So we really want to be able to do that. As I say here, we risk burning out people. I can't go to every one of these events. Neither can the people like Bruce, Dave, etc., who are doing this. And so event leaders have to consistently scramble before every event, which is what's happening right now. Let's send out something a week ahead. No one's responding. Send out something a few days again, trying to get people to come. So it's a challenge. All right. You've heard me enough. All right. What's happening in the near term? You have Discovery coming up at Sutton County Historical Center. So we do have quite a few people helping out with that. So thank you all who have signed up to help with that. If you want to add yourself to that, Don Nab is actually the event leader for that. So he'd be the person to contact. Now, March 5th, we have a STEM night at Greenwood Elementary. Right now, I have only Baker has basically said he would help out. I'm going to be there. I'm going to have 2 tables inside. I want at least 3 or 4 people outside. I probably need 5 people or more to help with that event. So I seriously need help with the March 5th event, which is before our next meeting. So if you can help me with that March 5th event, please get a hold of me. And then the March 7th, we have a Chester County Parks Night event as well with Rita as a park ranger. And so this is actually jointly with Delaware Valley and Astronomical Association. Did I get it right?
Amateur shot.
Okay, amateur astronomy. All right. So this is something where one of a few times we've actually trying a joint event. I don't want DVAA actually having more people at this event than we did. This was our event, and then they were added on. So I really want to have enough scopes there so that we can be the people who are running the event. Does that make sense? So please consider these. I will send out something tomorrow to the club, everyone in the club, asking for your support, especially these near-term ones, but throughout the year. Any questions? Yes.
Generally speaking, what is the involvement of people who come to, help out at the events? Like, what's that look like?
Involvement can be anything from you bring your telescope, and you're basically focused on an object or two that you want to observe that night, and have people come up and talk to you about it. Or you can be somebody who's just pointing out the night sky to people. We need people who are helping people with binoculars and how to use binoculars and how to look for constellations. It's great to have somebody who can take people off and actually talk about the night sky and sort of give a little sky talk. It can be any of those things. Before the events, a lot of times when we're setting up, I'm trying to set up my scope, or Pete's setting up his scope, and all these people are coming up because it's still light out, and they're like, "What's going on?" And you're trying to set up a scope and get it all aligned. So if you can talk to them while we're setting up, even if you don't have a scope, that's very helpful to us.
Or even just helping like at the table to help give out information.
Yeah, we'll have club information. During the daylight, I'll try to bring like a poster that people can interact with. We'll talk about maybe some games that kids can play. So there's things like that you can do to engage people that give basically a space theme and show we're really engaged as a club.
So even if you don't have a telescope, you're useful.
Absolutely. All right. So thank you, everybody. And solar events start in mid-March.
Okay, Bruce, you can introduce.
So hi, everyone. Thanks for coming out during our little thaw here. I'm sure you agree, we all have chaos in our lives. I know I do all the time. And I would think, given situations that we're living through right now nationally, it's a lot of chaos. But I didn't realize until not too long ago that chaos is a real deal. I mean, chaos theory is a real branch of science and mathematics. And essentially, it describes a system that's predictable in principle, but unpredictable in practice. So, in other words, even though the system follows certain deterministic rules, its time evaluation appears random. So, tonight, we're going to have a talk on chaos theory. And again, this is a real deal. This is a branch of nonlinear dynamics. It's been invoked to explain a lot of complex systems, from weather to fractals, and as our speaker will talk about tonight, to certain astronomical and planetary features, including the motions of some moons and the behavior and activities of black holes and neutron stars. So tonight, our speaker is Dr. Becca Phillipson, and she is a pioneer in the study of chaotic variability and non-linearity in astrophysical systems, especially those that involve objects like black holes and neutron stars. So Becca did her master's and her PhD at Drexel, then went on for a postdoctoral position at Washington University, and for the last 2 years, she's been at Villanova as an assistant professor in the Department of Physics. For someone of her age and status, she has a very impressive research career. She runs the Phillipson High Energy Astrophysics Group, and she'll talk a little bit about that in her talk. And in addition to a really active and dynamic research program, she's also very much involved in mentoring, which I find this very refreshing that young faculty in the sciences considering mentoring like a real vocation and not just something they have to do that the administration tells them. And so she's actively mentoring the next generation of astrophysicists, and she involves them in her research projects and publications. And she's also engaged in science policy and public outreach, including serving on the American Astronomical Society Committee on Astronomy and Public Policy. So it's a real privilege and honor to have Becky come here, and she's going to discuss chaos in the cosmos.
Up a little bit. They can see you.
Okay, that's Zoom.
Yeah, they can see you.
Great.
Before
Is this-
Becca starts, if anyone wants snacks, we got cookies and pretzels and chips and water and stuff.
Need water?
Help you out.
All good. Is there any mic or anything I should be speaking into up here?
No, the mic,
You good?
the mic is in the webcam.
Okay, perfect.
Okay.
Got it. Okay.
What it did like.
Just let me know if you need me to speak up. I'm happy to do so.
With the lights one's different.
I think this is okay.
Okay, all right, good.
We'll find out if we need it. Somebody I'm sure will shout out. All right. Thank you so much for that introduction. So I am going to be talking about chaos, and I chose this particular title slide because what we see here is you might think some kind of astrophysical system. Maybe it looks like an accretion disk, or maybe there's two things that are orbiting each other with plasma around it. In reality, this is a mathematical object called the Lorentz attractor and is a chaotic system. And I chose it because it happens to look kind of astro-y, right? But we will get into, or at least I will get into, how that relates to the work that I do in my research. So a few things that we are familiar with, hopefully. Weather, I think, is certainly top of mind the past few weeks. And weather is unpredictable. It's pretty canonical. I think everyone's had that experience where you're like, 10 days out, I know what the weather's going to be. It's going to be 50 degrees. Or, oh, the chance of snow is at 90%. And then that slowly ticks down for a bit as you get closer to it. Now, there is a certain horizon or time horizon at which we're good at predicting weather. And basically, beyond 5 days, it sucks. Within, as soon as you get closer and closer, it gets better and better. And that phenomenon is not because of how tech savvy we are, but it is because weather itself is a chaotic system. The ability to predict what it's going to do is very, very, very challenging. Another aspect is fluid dynamics. So this is basically turbulence in water. Another is population studies. So that's a rabbit. Oh, sorry. But the thing that it's on is called a bifurcation diagram. And basically what you're seeing is for a particular population size, as we change the rate of how we reproduce, what possible population sizes do exist based on that equation? And we see we can predict pretty well. Is this from the laser pointer? We basically have one possible population size, and now we have two possible population size, and this is called a period doubling cascade. You see, they double the number of possible populations, and then chaos happens, literally. And so this is a system that is also chaotic. It's very hard to predict the population of rabbits. That's actually, this model is to describe rabbit populations, interestingly enough. This is heart rate. In case you didn't know, if you have an erratic heartbeat, that can usually mean there's something wrong. But in reality, heart rate variability is not perfectly periodic. If you were to zoom in on heart rate variability at the doctors, you'd see the same pulses, but it fluctuates slightly. And the way that it fluctuates every peak, both the large chamber and the small chamber, is not precise in time or in amplitude. And the way that that changes over time is also a chaotic system, interestingly enough. So these are all hopefully things we're somewhat familiar with. The last one maybe is the stock market. We like to model that with predictive modeling systems. Really hard to do. And that's because it's not predictable. It is a chaotic system. So this is part of what makes it really challenging to predict what's happening in the financial world. And there are very sophisticated models to improve that, to improve probability of detecting certain changes. But in reality, the challenge there is because it is a chaotic system. So we're going to get into exactly what makes chaos, the exact recipe for it, and its parameters. And this is the origin of the popular, I guess, nomenclature for the butterfly effect. Something that happens on the other side of the world causes something else totally different on our side of the world. And maybe where one thing was a small effect, the flap of a butterfly's wings, the effect is massive, like a tornado in Texas. And that is also something that's related to chaos theory. So let's go to the basics, and that is with the Lorentz attractor. Edward Lorenz is often regarded as sort of the father of chaos, and he was a meteorologist. So we're back to weather again. And what he had was a gigantic computer, and that is a little sticker icon, but it is basically the size of a room, back in the 60s, and was computing some things in the upper floor at MIT's campus. Made a lot of noise. A lot of people didn't like to work on that floor, apparently, because it was so loud, this large computer. And what he found was he put in this model, and there's an equation basically that describes the weather, things like temperature, pressure, etc., anything you would want to know. And put the exact same parameters in, ran it twice, and these two runs were exactly the same and then started to deviate. And then far along, all of a sudden, we have two very different predictions. Again, this is climate, so big surprise. Two different predictions for the exact same initial conditions. So if any of you have seen the movie Hidden Figures, yes? Great. One of my favorite movies. And one of the mathematical algorithms that one of the main characters comes up with to basically confirm the orbital dynamics for an astronaut before they go to space, John Glenn specifically. And so before John Glenn goes into space, he's like, I got to call and make sure that before we launch, that I know exactly what we're doing and where we're going. She uses a method called the Euler method, and it's basically because the equations are hard to solve by hand, you use an algorithm to solve them. And it's basically like instead of you basically pull out a ruler and you're like, I only know the tick marks and I know, how long this thing is, but I only know it at the tick marks of my ruler. I don't know it continuously as you would if you had a pen and paper. So there's a method for kind of inferring the orbital dynamics of something that way using Euler's method. It is so precise that it's trustworthy to send an astronaut to space. This same method used on a chaotic system causes this effect. You would not want to trust that going to space. So what is the difference between what's happening in orbital dynamics versus the chaotic system of weather? And that gets us back to a few other maybe popular things in chaos. My favorite chaos theorist from Jurassic Park, of course, the butterfly effect. And so this idea that something so tiny happened between the first and second runs in the computer, which is the round-off error in your computer. So your computer can only handle knowing a certain number of decimal places. Let's say it's like 12 decimal places or something. That one decimal place, just changing it slightly in the computer, caused this dramatic effect. So that is where the butterfly effect comes from. So let's get back to this Lorentz attractor, this thing that's drawn in pretty colors. This is this little zoom in here is if you took one dimension here and plotted it, that's what it looks like. So you see that it sort of wants to repeat itself a little bit, but doesn't quite. That's what's happening in 2D here. And so let's actually think about the recipe for chaos. So this is something where this is my moment in my talk where I'm like, chaos sounds cool. And I'm about to tell you some math. All right. Okay. So we're going to spend maybe 5 to 10 minutes about math and geometry. And, Hang in there, strap in. I'm gonna walk slow. And then it will tie back to astronomy eventually, I promise. I know I'm talking to a bunch of astronomers, so we will get there. But this is the path we're going to take. We're going to learn about attractors, strange attractors, chaotic attractors, what that looks like, and then we'll look at some applications. So to start, something very familiar would be a clock. Let's say you have your clock and the thing that is ticking for the seconds, the pendulum here at the bottom of your clock. There isn't one in this room. I think we're all digital these days. This has to keep very regular time, right? If we want precise seconds, hopefully our seconds aren't changing, then this going to one side and then to the other is taking the exact same amount of time. It comes to a stop on the right side, it speeds up on the bottom, and then it comes to a stop on the left, and then repeats the process back and forth. And so what you're seeing here in black is exactly the position of that going back and forth. And then in red is how fast it's moving. So the position would be to the right versus to the left, back and forth. So to the right, to the left, to the right, to the left, to the right, to the left. And then the speed here is in red. Speeding up to the left, speeding up to the right, speeding up to the left, and so forth. So that's what's being shown in red. If you put these two things against each other, you get this circle or this ellipse. And what's very nice about this is you get a single circle. It's perfectly predictable. It has an exact shape. There's nothing fancy about it. A circle is a unique geometry. It's distinct from a spiral or a donut shape. And because it has this unique geometry, it's special, we can identify it easily. We can say any system that looks like a circle in what we're calling phase space here, if it looks like a circle, it usually means it's predictable for all time. Our clock hopefully is predictable for all time in terms of how fast it's moving. So these are related. We know what's going on in the system. It's predictable, has a certain period, and so does our circle. Let's add some friction to our clock. Okay, it's starting to break, and so our pendulum is slowing down. We see both our position is going towards this horizontal, and we're slowing down. The amplitude here is getting shallower and shallower. And so if we translate that into phase space, we see this spiral going in towards the origin. That is a distinct geometry from a circle. It's not closed. We know it's not coming back to itself. This never goes back on top of itself like it does on the circle. So we know it's not repeating itself. It's slowing down. And so a spiral is a distinct geometry from a circle. And so does a broken clock as compared to a regular one. And so we can infer what's going on in this system based on a geometry here. We can infer what's going on with our clock. Now let's get more complicated. Let's imagine we don't just have a clock that's slowing down. We have a whole host of other types of equations. We don't just have clocks, we have things that vary. So instead of varying position of our pendulum, maybe we're varying temperature or some other quantity or observable that we care about. There are a few types of attractors. So the thing that phase space wants to approach or attract to is where that term comes from, is some theoretical geometry. So in this case, this is our circle. You can kind of see it's like an ellipse, right? So you take any kind of clock, the one I showed there or anywhere on the world, you take anything that has a pendulum clock, you give it a ting, and then let's assume that it's a good clock. All of them will want to approach this circular path in phase space. And so all of them want to attract or become a limit cycle attractor. Anything that's like a spiral, broken clock, every broken clock that just slows down immediately after you give it a little kick, it wants to approach what's called a fixed point. Anything we give a kick, any kind of clock that's broken, it eventually slows down and comes to a stop. And so the phase space is universal. This geometry essentially is a fingerprint for types of dynamics, as we would call it. We have a whole host of types of geometry we can get in phase space. I have shown the simplest two. a fixed point, a circle. You can also get a donut. That gets crazy. So this would be, before we knew the sun was the center of the solar system, we had epicycles to try and explain why Earth is somehow the middle of the solar system. Trying to explain orbital dynamics with a torus was one approach. Not a good one, turns out. So we call those, actually I put it down here in the bottom right, non-strange attractors. The thing, a fixed point, a circle, and a donut, pretty approachable geometry. Once we get to strange, things get strange, as are very creative descriptors here. So let me see if this will play. Let's take a clock. Okay, imagine this clock is weirdly broken. Okay, there's a little monster that lives in the clock that randomly pushes on the pendulum. And then there's also friction. It wants to slow down. And those two things are constantly competing with each other. If you have what we call damping, that would be like that friction, and driving, that's the little monster in there pushing at it randomly, or little imp maybe, then we get phase space that looks really funky. And don't look at the math, be careful. There you go. This is just evolving it over time for a bunch of different types of damped and driven oscillators. So just like we had a bunch of different types of clocks, and they all wanted to approach the circle. If we take a bunch of different types, damped driven oscillators as they're called, you get this bizarre shape in phase space. And what we're starting to see is all these twisted lines. This should remind you of, maybe if I can go back, pause. Nope. Oh wait, I can use this. Nope. SNL.
Nice break.
Yes. Here we go. On my front page, I regret making this choice to go back in time. That should look like this. Yeah. So there is some connection to the geometry we're seeing. Fast forward. And what we are discovering is something that's called fractal geometry. So I want you to imagine if you took a string off a yo-yo or something else, and let's imagine that string is infinitely long. Okay, this is going to hurt your brain for a second, but imagine it's infinitely long, but also infinitely thin. And I look down at this table and I'm like, I'm going to arrange this infinitely long string on this table such that there are no gaps. I fill it all as though I'm basically making a blanket. And I'm fitting it on top of that table. Something that is a non-fractal dimension, this would be like a dimension of 1, a dimension of 2. We live in 3-dimensional space. Yeah, anything that fills the area of the table is 2 dimensions. So the table is 2 dimensions across the top surface. A blanket with no gaps, 2 dimensions. If you took that infinite string and kept filling it over this table for all time, but never filled the table, you left gaps on top of the table. That is a definition of a fractal geometry. It is a fractional dimension, meaning it is somewhere between 1, which is an infinitely long line, and 2, which is the square top of the table or a blanket. The fractal geometry is weird because oops, I went the wrong direction. The shape that we're playing here never fully fills in. I could let this go for all time for a damped and driven oscillator that's strange, and I would never fill up this plot. And so I would basically have a dimension between 1 and 2. That hurts the brain a little bit. This is a zoom in of that same phase space. If I were to zoom in and you kind of look, you see a couple lines here that are thick. There's like 3 from far away. If I zoom in, I see a bunch more. Basically, I look at my infinitely long string that I've assembled on the tabletop and take a magnifying glass. I could start to see where all the gaps are. And what you end up having is what's called self-similarity. I see this interesting structure and I zoom in and I see the same structure again and again, the more and more I zoom in on it. That is what we see in fractals. If you've ever Googled a fractal like a snowflake or any of these types of shapes, if you like zoom in on them, sometimes they're putting GIFs that kind of like hurts your brain a little bit. And it just constantly is zooming in over and over again. I think I have one. There you go. And you see the same thing over and over again. Well, hurts the brain, fractal geometry. You're in for all time always going to discover new open triangles. So fractal dimension between never 1 and 2, you're never filling a full area. So geometries that are fractal, or not fractal, rather, are these top rows. A donut, a circle, and a point. This is 1 dimension, 2, and 3. Somewhere in between is where we have a strange attractor. And then something where there's nothing going on, like static noise, that's pure randomness. That would be pulling a random number out of a hat. So this indicates there's no equation, there's no dynamics predicting something. Someone just being asked on the street, give me a number, and you plot it. There's no like reason for it, but everything else lives here. And so basically most of the universe lives in this realm. And we use a lot of approximations to make it easier to study by placing it here. Okay. So that is sort of strange attractors, very bizarre. And now we get to what about strange attractors gives us chaos. And it's a special requirement. That's this last category here. So we have one condition so far. We have an attractor. Our second condition is that the attractor or this phase space is fractal in shape, in dimension. And we're going to explore this last condition, which is what Edward Lorenz stumbled upon. And that is sensitivity to initial conditions. If you took his computer, he had some equation for the weather. He plugged in the same numbers twice and got totally different results eventually. What he ended up having was the sensitivity to the round off error in the computer. And so that 12th decimal place was just enough, even though it's tiny, 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 tiny number, was just enough to change the outcome after some amount of time. And so this is really, 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 really sensitive to what we're calling initial conditions. Basically, what did I put in the computer at the start? And if I changed it ever so slightly, the sensitivity to how different I get at the end is the sensitivity to initial conditions. So two things that start close to each other. This is the Lorentz tracker. So this was in one of just plotting one of the coordinates. This is plotting 3 of them. I take the same 2 trajectories that maybe start initially close to each other. If we follow them over time, they eventually deviate. And if you're doing that for any set of initial conditions, you get very, very interesting, beautiful shape and geometry. If you were to zoom in on that, if I took 2 lines that are really, really close to each other initially, and I zoomed in, you'd see one orbit goes away, the other continues on. How fast it deviates like that, or how quickly 2 things that start very close but then end up splitting. There is an actual number here. It's called a Lyapunov exponent. I'll come back to it later, but it's something you can actually measure. Okay, that is the foundation of chaos. How are we feeling so far? That was some geometry. Thumbs check. We're okay? Excellent. Okay. So our recipe for chaos. The second one we talked about is strange attractors and fractal dimensions. We've also talked about sensitivity to initial conditions. And this is where this famous quote comes from: chaos. When the present determines the future, but the approximate present does not approximately determine the future. What? Yes. Basically, it's really hard to predict the future. And if you're approximately correct, you might be very largely wrong later on. So let's get to the last requirement, which is this word nonlinear. And in your introduction, you reference chaos theory as part of nonlinearity and nonlinear dynamics. Okay, but what does that actually mean? So I'm going to tell you, because even with my students, they forget what the difference is between linear and nonlinear, even once they've gotten pretty advanced math. Okay, so let's talk about a linear relationship. linear comes from the word line. We have a straight line. So if there's two variables plotted against each other, X and Y, for example, if you march through their relationship, you see it plots out a straight line. It's not bending or curving. This might be the price of your house based on the square footage. And that is some relationship where this, A out front is just some number, constant. I multiply some number by my square footage, and that'll give me a prediction on the price of my house. Something that is not linear is nonlinear. Basically, everything else that doesn't relate to each other in this linear way or in a straight line is nonlinear. So this would be x squared or quadratic relationship. If this were square footage and price, that would be disturbing because then it would turn over. Oh no, really, really big houses are really, really cheap apparently. So that is not true. That would be describing some other system that turns over eventually. Or something that's cubic, has a wiggly shape, and so forth. So these are all types of functions and types of shapes. And these are all under the class of nonlinear. And so when we have something that is a nonlinear equation, it means we have some term in our equation that is not just a constant times an observation. So these are, I think these are the only equations I've shown. These are the Lorentz equations that he plugged into his computer. Don't worry about it. The only thing I want to show you is this stuff in red. Those are nonlinear. So it's not a constant times a variable. It is two variables multiplied to each other. That is by definition nonlinear. So Lorentz stumbled upon, in creating the Lorentz attractor, the entire recipe required for chaos. We had nonlinear equations, plotting them in phase space as it's called, got fractal geometry, and that fractal geometry is very strange, and sensitivity to initial conditions when you ran it multiple times. All right, we have officially covered the theory of chaos. We're all experts now. I dub thee as experts in chaos. Now we're going to get into how do we study it. It seems really complicated, but I'll give you a couple hints. Sensitivity to initial conditions. Do we see that? That's one way to study it. Fractal geometry. That's another way to study it. So these are things that we actually have tools for. So this is not Lorentz. This is actually an observation of a star, or at least the equation for predicting how the magnitude of a star changes over time. For something that's chaotic, and we have a bunch of zeros and then a 1, and just introducing this tiny little number changes the outcome. This is a chaotic system. So this is telling us the model we're using to predict the brightness of a particular variable star is a chaotic one. We predict very different outcomes for the magnitude far out. So this is, and I mentioned this earlier, I said Lyapunov exponents. That's basically how quickly do this blue line and the black line deviate from each other. That's called a Lyapunov exponent. It's because it is an exponent. So that's one way we can study chaos. Find the Lyapunov exponents. It's positive. If it's positive, they deviate. If it's negative, they're like the donut or the limit cycle or the fixed point. They want to go to an attractor. Another is fractal dimension. How do you find fractal dimension? Let's take Great Britain, the whole thing in Scotland. If I were to take just the shape of it, which, side note, coastlines are considered fractal. Fun fact. But let's go with this island then. And we stick graph paper down on it. And I know the exact size of every square for my graph paper. And I say, how many boxes of my graph paper covers the UK? I count that, and I put it here, and my purple dot is. Okay, I know the size of my box on one side, and I know how many I needed. And then I shrink the size of my graph paper. and I do it again, like this red dot, and so forth. You plot those two things against each other, you get a linear relationship. It's a straight line. All right. The slope there is the dimension. So in this case, it is not 1 or 2. It's a fractal dimension. The slope here is something like 1 point something. That tells us UK coastline is fractal. Very cool. But that's how you, in practice, calculate a fractal dimension. It's a very straightforward technique. This is sometimes referred to as the box counting dimension. Very creative. Okay, so those are two traditional methods. Is you can easily plot sensitivity to initial conditions, but this is assuming you know the equation, right? You just run the equation twice, like Edward Lorenz did in his computer, and you're like, okay, I just give it the same initial conditions. I know they're going to vary slightly, and then look at how they change over time. That is basically empirically testing it. Another is measuring the fractal dimension of your data. A third method is something called what I'm dubbing topological, and that has more to do with geometry. And it's just studying the phase space directly. These previous two methods required running a model a bunch of times and kind of like testing out how things deviate. This one is computing the fractal dimension. Let's get into what is topology. Okay, this is what I use, and this is a side note. This is where my area of research is in. So I'm happy to field questions more on this. But if we go back to our clock example and our perfectly regular clock, and we saw the circle, and then we had our dying clock, and we had the spiral, all right? Rather than actually measuring orbits and how they deviate from each other, or directly computing the dimension, we can instead just look at the spiral and the circle and be like, they're different. That is topology. There are a lot of strategies for identifying differences in geometric structures. So one of them is something called the recurrence plot. So this is the Lorentz attractor. Woohoo! It has 2 orbits. And for every single point along it, and you can imagine you can do this with real data. I look at every other data point and I ask the question, are we neighbors? So here's my reference time. Here's some neighborhood of what I'm considering close. And here's another point, and I'm asking, hello, are we neighbors? And the answer to this question is, well, we're both in the same neighborhood, so yes. What about this point? Well, that's not in the same neighborhood, so no, we're not neighbors. So we're basically asking a binary question, a yes-no question. Are we neighbors or are we not? And we're doing that for every single point in time.
How do you define the neighbor?
Good question. Trial and error, and there are a lot of ways to do it. I'm going to gloss over that question. You can ask me at the end. If you repeat this for all time, so every data point here represents a point in time, compare every point in time. This is basically like a sonar map of neighbors. We see very interesting structure and behavior that's representative of this sort of almost repeats itself nature of the Lorentz attractor, represented by these lines. It's like, oh, these seem to be a very consistent pattern, and then it changes. We seem to have a very consistent orbit, and then it changes. So there is information that's contained in this QR code looking thing that's retaining the same information geometrically speaking or topologically speaking as on the left. Okay, let's give a more concrete example. Let's take the lyric from the song Barbie Girl. Okay, this says on the bottom, I'm a Barbie girl in a Barbie world. Okay, on the bottom, every box is each word. And same thing vertically. I'm a Barbie girl in a Barbie world. Okay, what I want to point out to in that lyric is there's 2 words that appear twice. A and Barbie. And they appear in the same order. I'm a Barbie girl in a Barbie world. This corresponds to A, and this pink box corresponds to Barbie. And they formed a line. If we go back to here, this tells us these lines are when something's repeating itself. It goes around this circle twice for each of these, or multiple times even, but eventually goes away. So the lyric here, or this segment of the lyric, repeats and repeats in the same order. If I repeated this entire thing a bunch of times, I'm a Barbie girl in a Barbie world, I'm a Barbie girl in a Barbie world, I'm a Barbie girl in a Barbie world, you would see a bunch of pink lines telling you that there's some repetition going on, or more mathematically, recurrence going on, which is where the term recurrence clock comes from. So we can use topology, which is basically our sonar map of geometry. We're describing the overall structure in geometry in phase space. Or we can get into the nitty gritty of what is the exact fractal dimension with sensitivity to initial conditions. This is our toolbox for studying chaos. So let's actually look at how this shows up in astronomy. And that's what you all are here for, but hopefully having understanding of the math makes it that much more intriguing. That's my hope. So the very first example of chaos showing up in our solar system is the moon of Saturn, Hyperion. Has anyone heard of Hyperion before? Yeah, great. Okay. One of the first ones, at least to be studied and chaos to be confirmed. So this article in 1984 predicted a model. All right, and I did block it out so that you wouldn't get freaked out. But there's some equation here, and they're like, I think if I took the axis as an oblong asteroid, I have the long axis, and the whole thing is tumbling, and I'm going to say the rate at which it tumbles is chaotic. So that was the prediction in 1984. And the follow-up to that was that because there's changing albedo across the surface of Hyperion, we should also expect when it turns and tumbles, the brightness should change. And how that brightness changes should also be chaotic because it's directly related to the axis of tumbling. In 1989, Claviger, for their thesis, confirmed through 13, I think, months of data collection from Chile and Arizona, photometric observations of Hyperion's brightness, and was able to confirm that this equation that I blocked out actually predicts the brightness of Hyperion. This was probably the best prediction or demonstration of something evolving chaotically in the cosmos. So this was in the 80s. Prior to that, some of the examples of chaos was Edward Lorenz, climatology, and then some other weird math equations that show up in laser systems. So the fact that this was showing up on astronomical timescales, describing astronomical systems, is actually a very, very big deal because this is happening in nature, not because someone's tweaking a laser. Another place this shows up is in pulsating stars. So there are some stars that vary in their brightness, and this is little m that refers to magnitude there. So this is what's called the light curve of R-Speedy. And these are individual observations. And what we see is kind of a smooth, kind of filtered circle here where you see these ups and downs. If you actually took the derivative or the velocity of how that's changing over time, apply those two things against each other, you would get phase space and it would be wobbly. But you'd have some kind of repeating behavior, right? It like almost repeats itself. So this is sort of hallmark just by looking at it. Looks like it might be chaotic. They actually found the fractal dimension of this observational data, Buechler in 96, and confirmed that that was chaos in that method. So that's the traditional method of studying chaos. Really strong indications. And then later in 2004, applied the same technique to a bunch of other variable stars and found the same exact thing. And so what this was indicating was that the pulsations of these stars, the fact that the brightness is going up and down, is a consequence of oscillation modes of the star. and that oscillation is chaotic. I mean, the classic example of a chaotic system is one that's an oscillator, like our clock, right? That pendulum is another term for that is an oscillator. One that's keeping perfect time is a simple pendulum or simple oscillator. One that starts getting that damping and driving weirdness, that's where we start to get chaos. And so the pulsation and vibrational modes of the star are vibrating chaotically. That gives you an indication, and this is going back to what I highlighted before, nonlinear equations. It gives us an indicating of how strong each term in our original equation might be. And this is very important if you want to find what is the dominant physics that's leading to the observations we see. You need strong hints of what those things are. And if you can use chaos to point the way, then you can rule out a whole other host of equations that might explain what we're observing. Okay, and then we get into my personal favorite object. This is a black hole system. GRS 1915 plus 105 is a black hole, and it has a regular star companion. This is an artist rendition, in case you're wondering. So this is an artist rendition of what's called an accretion disk. So the black hole here is at the center. This is hot plasma orbiting around it. It is sourcing that material from a companion star. And these two things are closer together than our sun and Mercury. So very, very, very close. And in fact, most X-ray binaries, as they're called, because the plasma here emits in the X-ray, most of them are very small orbits. So this one in particular takes a few days for these two things to orbit around each other. Some X-ray binaries, as they're called, where one's a black hole and one's a star, one's a neutron star, and the other's a regular star, orbit each other as quickly as in 10 hours. So they're very close, very energetic. This accretion disk is very, very hot. There's also a magnetic field in there, which launches what we call jets. And jets are basically along the spin axis. So if this black hole is spinning, you imagine it's whipping up material. And because there's magnetic field lines, those magnetic field lines are getting twisted. And so all this hot plasma is basically being funneled up these jets. And they emit very, very brightly in radio, in gamma ray, and an X-ray. And sometimes an optical. These are nature's, or rather the cosmos' natural particle accelerators. They're far more energetic than the particle accelerator at CERN or elsewhere. Really, really energetic system. If you imagine that the accretion disk is really flat and well-behaved, maybe you could model it like a spinning top or a dreidel. You give it a spin, you look at the top of your spinning top, and maybe it's spinning perfectly, and you get a simple pendulum type behavior. Or you give it a little bit of a warp, and then that period starts to wobble. That should make you think of a damped and driven oscillator, especially when you have a magnetic field and a companion star that's the little monster in your pendulum clock, giving a little bit of a bump or slowing things down. Okay, what is this? These are 12 different observations of GRS 1915 at different times. What do we see going on? Well, good question. We have stuff that kind of looks like a heart rate down here. My colleague Joey Nielsen dubbed this the heartbeat state. And we see it arrive a couple times here. Again, these are at different times. And what you're seeing is the brightness vertically, and about, which is 3 kiloseconds, so like 5 minutes or so of time, a few minutes. So we see these really, really strong variations in brightness over the course of thousands of seconds or less. And then we look at another point in time, and we get these weird dips, and a little tiny outburst in the middle. And then we get this really erratic behavior here. We have erratic behavior and then this weird quiescence, and then it goes back to erratic behavior, and then noise looking stuff. This is very noise-like, nothing interesting. This is all the same system. What could possibly be going on? Well, it's chaotic, turns out. And what's happening is, if you imagine phase space, where we started with our regular clock and we had a perfect, beautiful circle, and then we had our broken clock and it had the spiral, what changed? Well, at one point, we had something well behaved, nothing's going on. The second point, we introduced something that started slowing it down and adding friction. In this case, for our black hole system, the magnetic field increases. The radio emission increases. That jet that we see is changing its size and its brightness. And that jet is very, very, very powerful. The one that's launching particles into space. If that is connected to the disk in some way, then you can imagine that there's some kind of feedback going on between the jet and the disk. And so as the magnetic pressure is increasing or decreasing, as that jet is being launched or being suppressed, then we have an interaction or a change from something that's like a perfect clock to something that is more like a spiral or slowing down. And we confirm that by finding in 2000 at least, the fractal dimension. In some of these states, we found the fractal dimension was normal, like a 1 or a 2. In others, it was a fraction. Sorry, not the fractal dimension. The dimension was fractal in one case and not in another. We found sometimes it was periodic, like a normal clock, and sometimes it was not. So there's something fundamental in the system changing, where in one case it's a normal system, in another case it's nonlinear and has all the recipe to chaos. So knowing that there are parameters that can change and that we're looking for a specific recipe, Bellani in 2000 was able to identify 4 of those states that I showed were chaotic. Several were periodic, like the heartbeat state, and a few others were noise-like or random-like. And that would be more like random eruptions coming from the system. So this is a canonical example of chaos showing up in a black hole system. But also by identifying that it was chaotic, we can infer the relationship between all the different components of the system and when one is dominating versus not. This is further evidence, and that is the same object looking at its brightness over time. I don't know if you can see that, it's kind of faint. It's fairly erratic, but this baseline here is over about 30 years. And what we see is not only on individual snapshots, which are on the order of minutes, we also see really erratic, chaotic behavior over very long time frames as well. This self-similarity should remind you of those weird fractals where you zoom in and you get the same behavior again. Now, instead of it happening in space, this is happening over time. A long time scales versus short time scales. And we're finding the same thing, so these are the same states, but now instead of computing the fractal dimension, we can do that with the topological method. So the I'm a Barbie girl method. Using the recurrence plot, this is over the long term, the one I was showing you before. And these are 3 of the snapshots on like the minutes timescales in its recurrence plots. And what we find are the patterns of lines here. Those are distinct to whether it's chaotic or periodic or neither. You can do this with a neutron star. So this is a neutron star's brightness over about 20 years. And so this is a time series, meaning its brightness over time, or its flux, X-ray flux over time. This particular system is what's called a low mass X-ray binary. So it's a neutron star, and its stellar regular star companion is like an M dwarf, really low mass star. And it's in a pretty tight orbit. I think its period is like a couple days, maybe. But what's unique about this source is because it's a neutron star, it has a different profile for its magnetic field. And it has a very large disk as well. So it's slightly different than a black hole system. And looking at it over long term, we see that it wants to repeat itself, sort of. There is a periodicity there that wanders. It's about 120 days. So there is some global kind of precession going on in the accretion disk. And we can kind of confirm that this is phase space. So this is the same as if we took our pendulum and plotted its speed versus position against each other, and we got a circle. For this object, we get this kind of double weld behavior. And then this is its recurrence plot. And we see for something that's perfectly periodic, a perfect clock, we would have perfect straight lines, evenly spaced. We don't quite have that. We have a wandering period. That is what's called a super orbital period, meaning it's much longer than the orbital period. That 120-day precession is showing up in the way that these lines are varying in their distance and length. So recurrence plots are really fun to show people, especially scientists who like to do analytical things, because they're like, I want to analyze those patterns. Anyone that's like a postage stamp collector loves this. Let's create recurrence plots of a million things and see what all the consistent patterns are. Well, that should remind you of a really good task for machine learning, which it is. And so I'll come back to that in a second. But what I will say is we can confirm that this is chaos through another topological method. And it's basically comparing the phase space of the geometry here to a theoretical system. And there's an oscillator called a Duffing oscillator. And it has, for our recipe for chaos, you can create chaos with the Duffing oscillator. It has nonlinear equations for the right parameters. You have some knobs you can tweak to create sensitivity to initial conditions. When you plot its phase space, which is here on the right, you get a fractal geometry. So it has everything we need to cook up some chaos. And we can directly compare the geometry here, which I won't get into, but to using something called winding numbers, you can directly compare the geometry here to the real data, and they're identical, which tells us, hey, the Duffing oscillator equation might give us some hints about what's going on in this system. So this is a Duffing oscillator, like a desktop, tabletop version. And what it is basically two magnets, stick two magnets on a rigid frame. You oscillate that frame back and forth, and in between, you have this beam that can bend, depending on how stiff it is, and depending on how fast you're moving this, and how strongly, and how strong your magnets are, you'll see that beam oscillating back and forth in a weird, wiggly way, in a chaotic way, to be more precise. And so we can take every component in this tabletop version and be like, okay, what was the exact combination of how stiff my beam is, how fast I'm moving my rigid frame, how strong is my magnetic field or my magnets, and compare each of these quantities to ones that might be appearing in our neutron star. And this is my neutron star and it's spinning. And whether it's spinning on axis or off, how strong is its magnetic field? You can directly compare those two things. And so we can develop a model for what's going on in our neutron star to explain our observations that way. And we're able to predict that we have a slightly oblique neutron star. It's precessing, so it is spinning rapidly like neutron stars do that lead to pulsars. So it has a spin axis that's slightly offset, has a bright spot offset from that axis. That's connected to the accretion disk through magnetic fields, and all of that varies chaotically. And we can predict how strong that magnetic field is on the neutron star and confirm it with observations. All that because it's chaotic. Okay, so I'm going to wrap up here. Ooh, a lingering thing. And give you some final, just going to leave you something to chew on, some final examples. Stability of orbits is another example of where chaos exists. So you can see this with resonances between, this is a exoplanetary system. So you can look at like the stability of different orbits. The three-body problem, if anyone's heard of this, that is a chaotic system. Oh yeah, you get craziness out. Galactic dynamics. These are the paths of stars near the Milky Way center. Also chaotic systems. And there's a lot more. And so I like to leave this really dramatic and like terrible and terrifying video at the end, just to freak you out. But the caveat being this is over a very long period of time. But all of that is to say, chaos exists and it's everywhere. It shows up in orbital dynamics, shows up in fluids and plasma, shows up in black holes, neutron stars, pulsating stars, tumbling moons. It's everywhere. And in our weather, of course, as we've come to realize and experience firsthand. So the last thing I'll just say is this is, of course, my area of research, and one of the fun things I've been working on lately is creating recurrence plots and doing machine learning and AI on the patterns to try and predict when something's being chaotic or not. And so I'm happy to talk about that offline. And okay, and that's it. And so I'll leave us with this fun little graphic of the orbits in our solar system. And we find that they're slightly deformed. And because this is more than just a 3-body problem, it's extra chaotic. And so we do have the interactions of all of our planets, their relative precessions and inclinations. And if we fast forward a really long time just doing our orbital dynamics here, yeah, we start to see some overlap of our orbits with other planets. Uh-oh. Oh no. So is there anything else you want to worry about beyond just our sun eventually running out of fuel in its core? We also get to look forward to the overlap of all of our orbits with other planets. Anyways, so that I'll just leave that playing. Yes. This is, oh no. So this is where the artist comes into play to show us in a very dramatic fashion what might happen.
Mars.
Venus and Earth. Oh. All right. All right. So I'll happily take questions now. Thank you so much for your time. Yes.
The most chaotic things we experience every day. Crap. You know, Google Maps or Apple Maps, they use chaos theory when they tell you you're gonna get somewhere in 3.5 hours.
Oh, good question.
It's amazing how it works, but it's so chaotic.
Yeah, I think they use crowdsourcing.
Okay.
So live information, I'm pretty sure, is what factors in there. Yeah.
You mentioned the thumbprints that you see with some type of systems and some that can be looked at the chaos. Is it the applied this that you're aware of to cosmic anomaly?
Not that I know of. Oh, sort of. So, it is my understanding that there is fractal geometry in how in like how galaxies and galaxy clusters are clustered, so to speak. So there are some techniques that's actually more in the realm of what's called information theory. So when you're just thinking about fractals, that is actually what's going on in the CMB and also in kind of the clustering of on like the largest scale, the largest structure in our universe is there's definitely what's called multifractal geometry, meaning you have like different dimensions in different places. Really wacky.
For the CME, mostly in astronomy. So little tiny variations.
Yes. Right. The little fluctuations, yes. Yeah, I haven't done that myself, nor do I know anyone doing it, but there are other methods that are very robust for getting some of the parameters that are important for predicting the expansion. Right. So I think those are pretty much the gold standards right now. Yeah. Yeah.
So are there some systems or things that you may know of that you would predict they be chaotic that you plan on investing in? Like it's not known. You're just see, like for example, he gave you the example of Hyperion. I can think of many others from this bill. I would venture that maybe that acts in a chaotic system as well. Are you planning on, like, do you have those things in your mind? I don't know.
Yes.
Have any secrets or something that
Oh, no, there's no
that
secrets.
you want to look at and fly?
Yeah, so actually, so there's a lot has changed in the past couple of decades. And the biggest hurdle to identifying chaos in astronomy is the quality of the data. If you've noticed, basically what we're doing is a lot of observations over time and plotting them over time, which means you need repeated observations of the same system, because fundamentally what we are probing is how something is changing over time. And that means more than one observation. So we've, in the X-ray with like black hole systems, we first really got the chance to do that in the 90s with the Rossi X-ray Timing Explorer, which is an X-ray satellite. And it collected data for 15 years or so. And then more recently, we have some satellites like that, but that is limited to observations that emit in the X-ray. Now, what's changed recently is opening that up into other types of systems by having things like in the optical, for example. And the one that I'm part of is the Rubin Observatory. So the LSST down, which just launched, hopefully you all, some of you, and if you haven't, go look at the press release back from July, I think, of the Rubin's first images. Incredible. You could put a single image from the Rubin Observatory on the sphere of Las Vegas, and you still wouldn't be able to see the full definition of that image. It is that exquisite of a camera attached to a very large field of view. Everything, the works is exquisite, but its job is to observe the entire night sky that it can see. So like, I think 3/4 of the sky, basically, every single night, almost. It varies from 1 to 3 nights in cadence for 10 years. So you're essentially going to get a high definition movie of the night sky for 10 years. So anything that you could possibly see that exists or can be seen by Rubin, my intention is certainly to go data mining for chaotic variability. Yes. So, and there's a lot of potential in there. One that I've not studied but would like to are tidal disruption events. That's when a very unlucky star comes nearby a supermassive or intermediate mass black hole and gets tidally stripped and eaten away. But during that process, because it's getting stripped, you see the brightness, and basically it's essentially like if you're in the dark and you have a trampoline and there's a bowling ball on the trampoline, and you take out some marbles that are glow in the dark marbles and you toss them into the room, you can see the shape of your trampoline all of a sudden. It would be like doing that. That's what a tidal disruption event is doing. You're able to map out the geometry around an otherwise dark black hole that's otherwise not interacting with anything. And that kind of gets into kind of all of that accretion stuff I was showing with black holes. If you can get to know chaos around those systems, that would be really awesome. Yeah. But LSST, if you haven't looked it up, please do so. Yes, back there.
So, it's a real philosophy questions kind of thing, because there's like everything is kind of this kind of chaotic. So in this type of chaotic thing, like how the universe comes up with like life form, which is like so perfect.
Yes. Okay, I'll amend what I said and say the potential for chaos is there. As we saw with like the black hole system, those 12 snapshots, sometimes it's well behaved. It's the same system, and sometimes it's chaotic. What was changing in the system? Well, something that's chaotically varying decided to dominate for a little bit and then went away, or something that was very periodic. You know, the motor on our very regular clock was very strong, and so it overcame any kind of wiggles. So looking at the comparison between what's dominating a particular system versus not is the important question here. When there's a balance between competing forces, that's when you get chaos. So when you have both something driving your pendulum and something slowing it down at the same time. And those two things are in constant tension. That is the realm of chaos. When one of those things is dominating, you either get the circle or the spiral. So you get a very well-behaved shape, so to speak. It's when those two things are in competition that you get weird or strange behavior by definition. So in the universe, it's always that question is like, is there a dominant physical mechanism, in a particular system that we can observe? Or is there like a competing processes? And can we learn about how they're in competition with each other through chaos theory? But sometimes it's useful in that context. But sometimes if something's dominating, then you can very readily observe that through other means. Does that help answer your question?
Chaos comes to explain some dark energy.
Yeah. I don't know. And I think it's probably because nobody knows what dark energy is. That's the big question, I think. Good question.
You showed that orbits of the planets are actually in our solar system also chaotic. We have a mission going to Europa. The
Yes.
assumption is that there may be life there
Mhm.
and that it's been in a condition that's stable for billions of years, just like we've had on our planet, which would be conducive to forming life.
Yes.
Have you looked at, or has anyone looked at the chaotic behavior around Jupiter of all the moons? And is that really stable? Has it been where it is now, or did it maybe go into a very high magnetic field environment? And is it something that really would be conducive to life?
Excellent question on all fronts. I will say I'm not an astrobiologist, so there's a lot in there that I can't comment on, or planetary science rather, because there is the effect of like the heating effect from being with the proximity of Jupiter or Saturn, that compensates for its position relative to the sun. I would say the fact that there are rings should be alarming because those rings are debris from collisions. At the same time, this is far after a lot of orbits have been settled. But that's not to say that there aren't ongoing collisions. So it depends on if Europa is in a path that is cleared, like an orbital lane, essentially, which does happen. And whether there's a strong probability of that overlapping with Sylvance. And I don't know the answer to that.
Swimming out of going around.
Yeah, well, they're not random because there are resonances. So it depends on the reliable or the stability of those orbits. And if you're in a stable orbit, you're in a non-strange attractor, essentially. But if you're in a non-stable one, that's where the danger is. And I don't know the answer to that question. I assume people have studied that though.
Thank you.
Yeah. I would hope so.
Can you apply a lot of the equations and so forth for chaos theory to quantum systems? Or has anyone quantum physical systems, or does it break down? Like,
there is some breakdown there. If you get into the quantum mechanical realm, yeah, it changes. This applies to dynamical systems. That being said, laser systems are approaching that limit. And so there's a lot of chaotic dynamics studied there. But that is right at the edge of my knowledge. I don't think it is a viable option right now because of the probabilistic nature of quantum mechanics. Great. Thank you for your attention. I'll leave that. Okay. I'm not sure how to get outside.
Nice job.
Okay.
Okay, now I really got something to think about when we go home and get some dinner. It's actually had on this one for a while, but thank you very much. Fascinating talk, and I think that all of us, when we think about how most of us came and became introduced to chaos theory through Jurassic Park. Here we are applying it to the cosmos. It's just incredible breadth of this relatively new area investigating the universe. It's great. So, where's Bruce? Oh, there he is. He's chatting. So anyway, hopefully this really cold weather will break for us. Everybody, please take a look at the observing list coming up. I know it looks a little daunting at first, but don't forget, we don't need a whole lot of people in one or a whole lot of people in all of our observing events. We just need a few to help us out in key critical areas. And even if you don't have a telescope or binoculars, you are still useful. We can definitely use your help. And you have the time and you look at your calendar and you can put your name up on that list. I will appreciate it. Bruce will appreciate it, and especially Don. So we'll look forward to next month's meeting and we hope to see you here. Thanks again.
Kathy, could you hear me?
Yes, can you hear me?
Yes, all right. I found the problem with the
Okay.
sounds. You
Okay.
gotta, let's know for next time. It was
I
all in
was
the
gonna say,
system
make
up
a
there,
note.
the machine.
Yay.
Yep, got to figure it out.
Okay, good.
Okay, good.
I'm out of here. Have a good night.
Okay, see you. Thanks.
Okay, thanks, Don and Dave and everybody.
Fascinating group. Thank you.
Oh yeah, that's pretty cool, Dana.
Yeah, it was cool. It's the only thing that
Cool
keeps me
stuff.
awake this time of night. If I was watching television, I'd be snoring.
Sorry.
I'm due with my membership fee.
Okay, and you are.
And 10 months.
Oh, I thought you were.
Yeah.
Okay.
I think I was talking with you regarding payments.
Yeah,
I want to pay in the cash.
that'd be fine.
If I
Perfect.
pay now.
Pay right now if you want. Sure, yeah. Regular member does 30.
Okay.
Yeah, sure, great.
Hi, I just want to introduce myself. I'm Larry McLean. I sent you an email yesterday.
Okay.
Zoom.
Yeah, I'll send it to you.
And yeah, you did, but I was so impressed by this speaker that I decided to show up. And I would like to join.
Okay,
It was
sure.
My membership
Okay, great.
application and
Larry said, right?
right,
Okay, good. Great. Welcome.
Thanks.
I'm Don.
yeah,
I'm treasurer. Okay. And did you meet our president up there? Great. White haired guy.
yeah, Dave.
Steve. Yeah. Yeah. That's just his wife over there. And my wife's the librarian. Pete there is the vice president. So good. Welcome.
Thanks.
All right, tomorrow I'm going to write down right now 30. You're good. Thank you.
Don Nab,
Dan.
Don, it was very well done. And I was impressed by a variety of things in it, not the least of which that I actually recognized several of the terms, out of several hundred.
Uh-huh.
Pretty interesting. I did not realize how much the fractal function does what it does for chaos.
Just so you know, everything you say is on the auditorium speaker system. So
Yeah.
keep it clean.
Yeah, well, that should be easy. I don't know enough to make it to be like in your mind. Oh, well, Don, thank you for hooking me up. We'll talk
Yeah.
soon. All right, man.
Remind me next month. I'll send you the invite again. Okay.
Yeah. Yes.
All right.
Yeah,
I
will.
got to shut it down here.
All right. Good.
All right.
Good night.
Talk soon.
Careful
All right,
on the ice whenever you find it. Find
All right,
it
see ya.
before it finds you.